Hi, Karan.
Hey, hi, Dean.
Hey, Karan.
Great.
So let's wait for 1 more minute, then we'll start. I hope you guys can see my browser.
Yes.
Yes, Dave.
Okay. Okay, fine. Let's start. So welcome back. I think it's week 11. So this is actually not last week. This is last to last week, and this is like more about like continuous random variables and generating random numbers and transformation of random variable. So today we're kind of covering that. So we are kind of looking at continuous distributions and a bit of few more distributions which I have not covered in lecture. It doesn't have like very deep insights. It's just there. You need to know it. Just kind of recap of concepts, and that's the plan for today. So like couple of weeks back, we looked at discrete distributions, and these were all of them which we discussed with kind of use cases. So we had Bernoulli, categorical, binomial, multinomial, Poisson, geometric. So this table is kind of summarizing the constraint or situation which guides us to choose a distribution. And this was the discrete case. Today also, like we'll try to do the same thing, but for continuous. Okay. So it's more like review plus couple of more distributions. Okay. So the first one is uniform. So if X is drawn from a uniform distribution between A and B, we write it like that. And the density function looks something like this, 1 by B minus A when X is between A and B, including boundaries. Otherwise, it's 0. And the PDF looks like this. The CDF looks like this. The next one is exponential. So again, X is drawn from an exponential with parameter lambda. And this is how you write it. The PDF looks something like this. Lambda times e to the power minus lambda x when x is positive. Otherwise, it's 0. So yeah, I mean, basically we are just varying lambda and seeing how the PDF and CDF looks like. So again, going back to our lectures, what was exponential and what was the relationship with Poisson, right? So for example, if you have some observation interval t and you're trying to like count the arrival of things, then the count of things is distributed according to Poisson. So that's the top diagram. But if you're interested in intervals, inter-arrival time between two Poisson events, then that is distributed according to exponential. And this was the distribution. So we kind of looked at the inside of how exponential came about from Poisson. And by the way, this formula you can arrive from multiple stories. This was from Poisson to exponential, but there might be other ways to reach the same formula. But yeah, I mean, this is the popular one. So you want to like, if you want to like model something which is continuous and positive, you can use exponential. Not just interval time, you don't even need to think deeply about it. For example, if you're modeling standard deviation, which obviously should be positive, so you can say that standard deviation is drawn from an exponential, right? So exponential is just this is a constraint x is greater than or equal to 0. So exponential can be used when you want to model something which is positive. Because in the end, these are like standard distributions. It will never perfectly align with what you want to do, but it kind of is an approximation. It's a model, right? So yeah, so if you want to model like something continuous, you can use exponential, a positive and continuous. The next one is Gaussian distribution. Again, the formula looks something like this. it has two parameters, mu and sigma. And X is drawn from a Gaussian with parameter mu and sigma square. This is how you write it, or like this. And in the plots, we are just showing that if I keep my sigma fixed equal to 1, and if I just change my mu, the shape doesn't change, just the location changes. Similarly, if I keep my mu equal to 0, and if I change my sigma, you can see that the location is at 0, which is mu equal to 0. And as I increase my sigma, the spread increases, right? And not every distribution has this separation of mu and sigma, such a nice separation of mu and sigma, right? Like we'll see like gamma distribution in the next slide, which is slightly cryptic in terms of how parameters behave. And a lot of distributions are very complicated in a sense that you will not be able to relate to, you'll not be able to intuitively relate to how you should modify the parameters. But yeah, this is Gaussian. And of course, okay, is this repeating? Okay, maybe it's repeating. Yeah, it is. So you use Gaussian when you want to model something which is unimodal first, or you want to approximate it through a unimodal thing. And the values could be from minus infinity to plus infinity. So if that's the case, you can use normal. And we have also seen in the recorded videos that so many things in nature can be Gaussian. For example, if you're just taking random steps forward and backward, right? And you don't even need to like have like a coin toss +1 -1. You can have like a random fraction, positive and negative from a uniform. And if you just see the final location, it will kind of form like a Gaussian distribution. And we had seen like a couple of more examples in the lecture. So actually normal distribution is very common, especially because of some theorems, which we'll see in maybe a couple of weeks from now. So normal is very popular, and a lot of things can be modeled as the normal distribution. Then we have central moments. So mean is just expectation of X, or average in terms of if you're looking at the data. Variance is just variation around a central tendency, which is mu in this case. Mu is the mean, but in general, central tendency doesn't need to be mean. It could be median also, which will have a different name. It will not be called variance. But there could be like multiple central tendencies, like you could use a median, which is less sensitive to noise and things like that. And then even the standard deviation, because you have used a median, and you can also use like absolute value and things like that. All those things will have different names, but everything is kind of capturing the spread over a central tendency. In this case, it's mu, but you could have median as well. It will have a different name maybe. Then there's something called skewness. We'll see in the next slide how it looks like, but this is the formula for skewness: expectation of X minus mu by sigma whole cube. Then there's something called kurtosis, which is expectation of X minus mu by sigma to the power 4. And this kurtosis, but what we always look at is excess kurtosis. So actually, the kurtosis of our normal distribution is 3. So we just really understand intuitively what a normal distribution is. So we always compare with respect to normal distribution. And we'll see in the next slide what kurtosis is. Okay, so first thing is skewness. So skewness could be either positive, negative, or 0. So if it's totally symmetric distribution, then skewness will be 0. And if it's like tilted towards the left, then it's positive skewness. If it's towards the right, it's negative skewness. So that's skewness. Then kurtosis. So by the way, this is excess kurtosis, not kurtosis. So this black distribution is your Gaussian distribution. And then you have orange distribution, which has a kurtosis of positive, excess kurtosis of positive value. And then there's this blue distribution which has excess kurtosis, which is negative. And what kurtosis tells us kind of is how heavy the tail is. By heavy, I mean how far things can be from the mean. So heavier the tail, the fatter the tail, or the higher the tail, that's called the heavy tail. And if the tails are heavy, for example, here the blue distribution has a heavier tail, right? Versus the orange distribution. So basically you can see if kurtosis is positive or negative, then the tail is heavier or less heavier relative to a normal distribution, this which is the black one. So that's what kurtosis is. And this is just a summary of a couple of things. So you don't need to remember it, it's just there. So you have mean, variance, skewness, and kurtosis, and you can actually derive it for simple distributions. And you can see that Gaussian has a skewness of 0 and excess kurtosis of 0. And you can see kappa minus 3, right? Because 3 is the kurtosis of Gaussian. So excess will be 3 minus 3, which is 0. So anyways, I mean, this is like summary of most of the distributions we have looked at. Okay.
Gaussian is symmetric because of this skewness and all, right? Third moment and fourth moment.
So Gaussian is symmetric because of formula itself. So if you apply x or minus x, you get the same thing.
Right.
Or
Which
so-
is causing, I mean,
yeah.
the third moment
Yeah.
and fourth moment to become
Correct.
zero, right?
Correct. So this is just a statistics which is telling you that. But yeah, that's it. This one we had not seen in the recorded video. So beta distribution, and it looks something like this, which is beta distribution at a location x with parameters a and b. So a and b is called pseudo counts of two events, like a coin toss or something. So the formula is basically x to the power a minus 1 into 1 minus x to the power b minus 1. And then you have a normalization constant, which is called a beta function. And a beta function looks very similar to, like, we had seen that partition, number of combinations of partitions, right? That one side of the partition is a units, other side is b units. So a factorial, b factorial by a plus b factorial, right? So a and b, if it's an integer, so this is basically called a gamma function. So if a and b are integers, gamma function equal to factorial function. But a can also be fractional, then the formula becomes the same thing. It is a minus a into a minus 1 into a minus 2 up to 1 or 0. Till a remains positive, or the thing in the bracket remains positive, you keep multiplying with minus 1. So a into a minus 1 into a minus 2 up to a minus whatever number should be positive. So that's gamma function. So this is just a normalization constant. And how? So one thing about beta is that it has support over the interval 0 to 1, which means that this x has a constraint to be between 0 and 1. So if you want to model something which is between 0 and 1, you use beta distribution. What is the most common thing which is between 0 and 1? Probabilities, distributions. So if you want to model a distribution, you use beta distribution. So if you have like a one-dimensional distribution, then beta distribution is a perfect fit to model that one-dimensional distribution. And it can also be seen as a distribution of distribution, right? Because the thing you want to model is a distribution. Beta distribution itself is a distribution. So eventually it's a distribution of distribution. Any questions here? Okay.
No.
So, yeah. Okay. So now about parameters A and B, right? So how it behaves, first thing is when A is less than 1, you'll get a spike on the left side. So you can see there are two possibilities on the, if you look at the spikes, there are two spikes. One is a red one and one is a blue one. Red and blue, first two. So both of them, A is less than 1, but in one case B is less than 1, another case B is equal to 1. And in both the cases, you have a spike on the left side. But in case of B is equal to 1, you don't have a spike on the right side. So if A is less than 1, you get a spike on the left side. If B is less than 1, you get a spike on the right side, which is the case for the blue one, right? And when A equal to B equal to 1, you get a uniform distribution. And when A and B are positive, the distribution is unimodal. And based on the proportion of A and B, because these are pseudo counts of two events, based on proportion, you will find a peak where that proportion lies. So the mode will be something like that. So this is the behavior of the parameters of beta distribution. One more thing about beta distribution you want to know is this extreme case of A and B less than 1. When is that helpful? Let's say you want to model the probability which is sparse. By sparse, I mean that either it's very close to 1 or it's very close to 0. Right? So, because if it's very close to 0, then the probability of one event is very close to 0. And if it's very close to 1, then probability of the other event is very close to 0. Right? So, if A is less than 1, it promotes sparsity of one kind of event. If B is less than 1, it promotes sparsity of other kind of event. And if both of them are less than 1, it promotes sparsity of both of the events. This is much more easier to visualize in higher dimension. We might look at one distribution, which is a generalization of beta distribution to higher dimension called Dirichlet. And that is much easier to visualize because we can think of like a vector of words in a dictionary, right? So let's say you have a dictionary, you have maybe 100,000 words in a dictionary, and you have a vector of probabilities of what is the probability of a particular word occurring on a text, right? Now, there may be a use case where you're trying to learn the topics. So let's say the topic is electronics or computer science or something. So if it's electronics, there are very few words which will have a very high probability for the topic electronics, right? So most of the words in a dictionary should have very close to 0 probability. So that is what I'm saying is an example of sparse probabilities. So when you want to promote sparsity, you want a prior which has parameters which is less than 1. So I hope the intuition of sparsity is clear. Any questions here? Okay, fine. So the next one is gamma, totally non-intuitive, but we just need to know that. So a gamma distribution at a location X has two parameters. One is called shape. Second one is called a rate. And this is the formula. It's very complicated, but this is the formula for gamma distribution. And when will you use a gamma distribution? When you want to model something which is positive. So earlier one was for between 0 and 1, beta, right? The domain is between 0 and 1. Here, the domain is positive. So when you want to model something when X is positive, you use gamma distribution. That's one option. There was one more option which was exponential, right? We have two options. Now, there are two parameters. One is called the shape and second one is called the rate. Both of them are positive. A bit more about the behavior of these parameters, because there's no easy visual way to look at it. Even I forget about how these parameters behave. But yeah, I mean, it's not like easy to remember for a long time. But yeah, this is how it behaves. So if A is less than equal to 1, then the mode is at 0. Otherwise, the mode is away from 0. So the domain is positive, that is 0 to infinity. So now if you see that when a is equal to 1 or less than 1, the mode will be positive. So there are only two cases when a is equal to 1, which is the blue one, dotted blue, solid blue. Both of them has a equal to 1. So the mode is at 0. Other cases has an a greater than 1, so the mode is away from 0. And the higher the a, the more away from 0 it will be. That's the behavior of a. Okay. The next one is the rate parameter, which is b. And again, you can compare the same colors for b also, right? So it's yes. So you can, if you compare blue with blue, you can see that b equal to 1 and b equal to 2, right? So for a fixed a, if b is increasing, the rate at which it goes down increases, right? For a higher b. Now you can see that this dotted blue line, a blue curve, starts at a much higher value and has a higher b relative to this solid blue. But it decays so fast that it crosses the solid blue and goes below the solid blue. So that's the decay rate in terms of what B does, and that's true for all the colors. For example, if you look at the red one, red dotted and red this thing, right? So again, you see that the dotted one has a higher B, so it decays much faster and crosses the solid red. And because of the height, you can also see that A kind of controls the amount of mass in the beginning. B controls the rate at which it goes down, but collectively it works together. It's kind of difficult to understand, but this is how it behaves. And another thing is, whenever the rate is higher, so we can just read this, right? As we increase the rate B, we reduce the horizontal scale, thus squeezing everything leftwards and upwards, which is happening, right? Just focus on the red curve, dotted and solid. The dotted red has a higher B, so it goes down at a higher rate, and because it should integrate to 1, there is no other choice but to have a bulge in this area, right? So that's about the parameters of the gamma, and you have to just remember the use case of gamma, which is it models positive quantities. Any questions?
Basically, it is controlling the skewness and the tail events.
Yeah.
I mean, heavy tail events can be modeled here.
Yes. Basically, you have control over it. You can say that.
Yeah, I mean, you see the high. I mean, if
Because there
event
are,
has
for example,
some.
if you had like real
Mm,
valued quantities, like positive and negative, there are more heavier tail distributions also.
okay,
So heaviness is relative, right?
right.
So yeah. So whenever you compare two distributions, then only you can say whether it's heavier than other or not. But yeah, I mean, I get it that
I mean, it could be one of the options. I mean, definitely there would be more ways
yeah,
to model that thing, right?
yes. And also a lot of times the options is so less that anything is fine. For example, the quantity should be positive. How many options do we have? Right? You can't use normal. You cannot use student T. You cannot use Laplace. So you cannot use a lot of things when things are positive, for example, right? So yeah. Okay. So one more thing is gamma distribution is also a generalization of things. So gamma distribution is a generalization of two distributions and maybe more. We have to check Wikipedia, but yeah, these are the two which is a generalization of gamma. So when shape is equal to 1 and rate equal to lambda, gamma distribution becomes exponential distribution, and it's very easy to check. You just substitute these values in the formula and you get exponential. Second category is chi-square. Again, chi-square distribution, you can see what is it in the bottom statement, but basically chi-square is gamma when shape is equals to mu by 2 and rate equal to half, where mu is called degree of freedom. Now, what is degree of freedom? So, degree of freedom is basically, chi-square is basically a distribution of a random variable. And what is that random variable? It is a random variable which is sum of square of standard normal distributions. How many of them? V of them. So you have V independent random normal distribution, you square them, you add them, you create a new random variable that follows chi-square. So that's what is the meaning of degree of freedom in chi-square. So basically gamma is a generalization of these two things, right? So yeah, that's that. And obviously it's very easy to see exponential is also for positive, and normal is negative and positive, you square them. So squaring anything becomes positive. Sum of positive things will be positive. So chi-square is also modeling a positive quantity, right? Okay. So now,
Then
yeah,
there would, I mean, uh, now there would be some relation between exponential and chi-square also. I mean, not directly, but hopefully should be some relation.
there
Since we
should
are
be
now
some
saying that
relation. Yes, there should be some
uh,
relationship, but you can figure it out or not. It's
uh-huh.
impossible or not to find a relationship. That's another discussion, but there can be some relationship because of something common.
You're right, right.
Yeah. Okay. Now there are two heavy tail distribution I wanted to discuss. One is student t distribution, by the way, relative to normal or Gaussian. So when I say heavy tailed, it's relative to Gaussian. So one of the heavy tail distribution is student t distribution. There's an insanely complicated formula. You don't need to remember it. But what you need to remember is Gaussian distribution is sensitive to outliers. And a robust alternative to a Gaussian can be a student t distribution. So if you want to build something which is more robust to outliers, you can replace a Gaussian with a student t. Now it has a couple of parameters. Mu is 1, mu is the mean, sigma is a positive quantity, and it's a scale parameter. And it's just a scale parameter, it's not a standard deviation. Sigma was the standard deviation in Gaussian. Here sigma is not the standard deviation. There's a formula which is a function of these things, which is the standard deviation. So scale is not a standard deviation, but sigma is called the scale parameter. V is greater than 0 is called degree of freedom. Now, yeah. So actually it's called degree of freedom, but if you kind of read about it and other things, you'll see that a better term is degree of normality. So this V or mu controls the degree of normality. Okay.
Hey, one thing before we
Yeah.
move on. When you're saying that Gaussian distribution is quite sensitive to outliers, now to be very specific, let's say normal distribution is symmetric, we know. Let's say assume I have outlier. I mean, what this statement tells to me is it statement telling is that my spread will become larger if I have outlier very far. And if, I mean, can you just
Spread, yes. So spread will
what
also change, but mean will
yeah.
change.
So you mean to say both mean and spread will change
Correct.
when I have outliers.
Correct.
And in case of if I use a t distribution, it won't change.
It will also change,
I
but it
mean,
will change less.
yeah, that was my vision. That will change less.
Yes.
Okay. Okay,
and
fair enough.
significantly less. Yes. A good intuition would be like when you do linear regression, right? So let's say you have like a cloud of points around a line, and there's one outlier point somewhere very high. Now, if you model it as a Gaussian, if you model the error of the line and the points as a Gaussian, you see that the line is not following the cloud. It is kind of deviated from the cloud because of that outlier. But for example, if you use student T, it will be just slightly deviated from the original line through the clouds, right? So that's another intuition where the outlier lies. I can maybe find, yeah. So actually wanted a, yes, this one, right? So you can see here, there's a linear regression thing, which is the blue line. And what linear regression means, should we open it? Yeah. So basically, yeah. So basically this blue line, so basically the data set is fixed. You have a cloud of point. Let's say originally this was the real cloud, and let's say all these points are outliers for some reason. Of course, it's a fake data set, but we can assume all these points as outliers. Now we are using different kind of methods to estimate the parameters of a linear model. So this blue one is actually following normal distribution. Then there's this Hubbard loss, which we will not discuss today. But basically, it's basically within a range, it's Gaussian. Outside that range, it's not Gaussian. That's how it's designed. But anyways, the point is that Hubbard loss is more robust to outliers, and RANSAC is basically random consensus sampling or something. But anyways, the point is there are various methods. There could also have been like student T regression, right? Now the point is there are various ways to estimate the parameters of these lines. Now you can see that this blue line, which follows a normal distribution, is very sensitive to outliers. And
Right.
as you make your distribution or loss function more and more robust to outliers, it does a better job of rejecting outliers in terms of when you estimate things, right? So
Right.
basically, when you do robust regression, you can do better than normal. That's what I'm trying to say. Any questions here?
No, I got your point. Yeah.
Yeah. So basically, the choice of distribution actually makes your model less or more sensitive to outliers. Again, I am not answering the question how to connect this to data. That we will look at after maybe 3 weeks. We'll start looking at how we can connect these things to data. But for now, just trust me that it is possible to connect this to data. Okay, so whenever you want to model something robust, like more insensitive to outliers, let's say, and you have this mu parameter which controls the degree of normality. I have not written the value of mu makes which okay. So it's saying that the larger the mu, no, sorry, v, let's say v, because we already have a mu. Because I think this is also called nu or something. But anyways, there's a lot of Greek alphabets. So this v, as you increase it higher and higher, it becomes more and more normal. Okay, so that's how you can control normality, like in terms of how normal it is. For example, v equal to infinity will be exactly normal. Not 100% sure, but I think so. The next one is, again, this is also heavy tailed. This is called a Laplace distribution.
Dave,
And
one
this,
more thing, one more question. Sorry. When talking about this student T distribution, one point is clear, sensitive to outliers, irrespective to Gaussian distribution. Now, let's say you look at data and you say, okay, boss, we want to use some exponential distribution. Now, it also contains some outliers. Is that this distribution student is alternative to that particular distribution, gamma or other kind of distribution where they
no,
have outliers?
no,
Or
because
it's just an alternative to Gaussian distribution you want to say
so
in
first
terms
thing
of
is, yes. So I'll just answer it. So first
uh,
thing, when you say something is replaceable by another, is you look at the domain. The domain of exponential is positive.
mhm.
The domain of normal and student is the whole of real line, minus infinity to plus infinity.
Correct. I mean, assume that let's say you take a distribution which has minus to infinity, and it will go some other distribution, not normal, and you are saying that it has got some outliers. So my question is that it could be alternative to that particular distribution, this T distribution.
So when I
Uh,
say something as
mhm,
an outlier, the data set
mhm.
will have outliers,
Yeah,
not the distribution. The
yeah,
distribution is more
that's.
fat-tailed because
Mhm.
it is allowing outliers to be modeled.
I got your point. My question is that just looking at this statement, the Gaussian distribution is quite sensitive outliers, hence we are using student T distribution. Now, if somebody says, okay, boss, we have some particular data set which have domain, let's say from minus infinity to infinity, and it got some outlier points. So can I say that, okay, this all for this distribution, the alternate could be a student distribution because that
Correct.
distribution is sensitive to. That's what I'm asking.
Yes.
Okay. Oh,
And hello.
Yes.
Yeah, and then what would be the trade-off? Like if you see in generally, like if then in every scenario where it is applicable, this T distribution should be better to choose than Gaussian, right? Like if outlier is the only thing. I mean to see if I have to choose between this Gaussian and T distribution and this T is giving me a robustness in terms of outliers. So will it not be the case that in it will be good to take by default T? So there should be some trade-off, right? Like between these two.
Yes, there will be some trade-offs. First thing is it has more parameters.
Mhm.
So you need more data to estimate it.
But like
Yeah, go ahead.
to if you take more data to estimate, then means this degree of freedom will is also increase, right? Then we'll start
No,
approaching
no, degree of
Gaussian.
freedom is in our control. Think of it like hyperparameter.
Okay. Then okay. So more parameters is one kind of
Yeah.
drawback.
And in fact, yeah, no, you can also learn it. Yeah, you can also learn it. It is also possible. So basically, if I like go full in as everything is a parameter, then it will automatically tune how heavy it should be.
Yeah, and if you can like any application, like I have difficulty understanding in exactly what this degrees of freedom is in like in a
This was the
scenario.
application, right?
Okay.
This blue line was Gaussian model. And although it's not true, but let's say maybe this red line, let's say this green line is the ground truth.
Okay.
Maybe the red line is student T.
Hmm.
Maybe the blue line is normal, right?
Mhm.
And I don't disagree with you. You can always use the robust regression. No problem.
Yeah.
But in the end, the best thing about real world data set is that you have test data. So you can obviously always check how you are doing on your test data. But I don't feel like there's a problem with always using robust regression. But optimization can be sometimes difficult. Okay, so mathematicians, so one commentary. So normal distribution is smooth everywhere. Student t distribution is also smooth, but Laplace distribution is not smooth. So when you learn parameters, the mathematically some distributions parameters are easier to learn than others mathematically. Even like normal distribution has like a closed form solution if you know your data. So the thing is that it depends. Like if you are like a researcher or something like 50 years back, closed form solution is the best kind of solution. It doesn't approximate, it's exact. But practically speaking, I don't think it's a problem. You can use anything. And you always have your test data to decide on it, right? Which one is doing better. But yeah, I mean, having some robustness to outlier might be a good idea. You had some other question also.
Yeah, this degree of freedom. I think you said we can learn it. So just I wanted to say, like, if I have a data set, a sample data set, if I want to do some inspection, like how I will go about understanding degree of freedom. Like variance, we can plot and see. Mean, we can get a numeric value. Intuition behind like this degree of freedom.
Yeah, so degree of normality is the intuition. Don't call it degree of freedom, call it degree of normality.
Okay. Degree of normality means like to what
How
degree it is closer
yeah.
to normal.
So higher the value of mu, the more normal it becomes.
Okay.
And if mu is infinity, it will become exactly normal. In shape, not in distribution, in shape. Yeah.
Got it.
And obviously, this sigma is also not standard deviation. So its own standard deviation will have its own formula and all, but the shape will become more and more normal as you increase mu. Not mu, let's say v. Another option for robust regression is not okay. You don't always have to do regression, but another heavy-tailed example is Laplace distribution. It's also called double-sided exponential, and this one is actually more popular than the other one. In fact, when you read about robust linear regression, underlying distribution of error is actually Laplace. So this is how the Laplace looks like. It has like an absolute value thing. It doesn't have a square thing. That's it. That's the only difference. So it has two parameters, mu, which is the location, v, which is the scale. So yeah, so Laplace distribution is basically used for robust linear regression. So one is like philosophically something is a robust linear regression versus the name robust linear regression, right? So almost all the time, robust linear regression means that you're using Laplace distribution to model your errors. So this is another example of heavy tail distribution, which is very popular, more popular than student T. Okay, so okay, so basically here we have couple of distributions, and we are trying to see what is happening. So first thing is Gaussian, which is this dotted black one. Then you have student T distribution in blue and green. And you can see degree of normality is 1 and 2 here. and degree of normality has increased from blue to green. So this blue thing is tending towards the black, which is the green one, right? So if you just focus on the black, green, and blue, you can see that as I increase my degree of normality, my distribution is going towards the black distribution. That's one. The next one is Laplace. So if you kind of really focus on this tail, you can see that this red one is above this black one, right? Not that visible, but the point is that it has a heavier tail, right? And with these kind of simple plots, you can see how heavy a tail is for a certain distribution relative to each other. And for at least for this example, you can easily see that student t distribution has a much heavier tail. But of course, I mean, you have to also like tune the parameters, play with the parameters and see which has heavier tails. But for the particular set of parameters, you can see that here, student t has a heavier tail, right? Because all of them have like a spread or scale parameter, which can adjust for the spread, right? But yeah, you can see easily how degree of normality is affecting student t. And if I had like degree of freedom equal to 50 or something, it will be almost hugging this black distribution, right? So that's the intuition of degree of normality or degree of freedom in student t. Okay. So here what we are doing is showing you how outliers affect things. So here you have like some histogram or some data set of which I have plotted the histogram, these bar plots. Then I'm plotting the distribution for this data. So Gaussian is this black dotted thing which is hugging this red one. So red and black are hugging each other when there's no outlier. Red and black. And then you have Laplace, right? So without outliers, this is how it looks like. Now in the second case, you have some outliers, so you can see by this histogram. Now you can see how the distribution changes. So you can see here that these outliers change the spread of the Gaussian a lot, the location of the Gaussian a bit, or a lot depends on your reference, but this black distribution significantly changed because of these outliers. But again, you can see student t and Laplace have not really changed that much. In fact, the mode is almost neighboring the mode of the previous case, right? Of course, I mean, the spread will increase a bit because of these outliers, but in the end, student t and Laplace, both of them are doing a good job of handling outliers. And this is like a unidimensional case of the same example I showed you for linear regression, where we are trying to find a parameter slope and intercept of the line. This is like a one-dimensional case of that, right? Any questions here?
If you look at this outlier, I mean, talking about the second part, the Laplace height, I mean, the fourth moment, I would say, kurtosis is of the Laplace equation, Laplace distribution is heavily tailed down. I mean, to look at the
Yes.
two graphs.
So
Whereas
everywhere
the
it's true. Everywhere it's true, right?
so I
Student t is
mean,
always
it's
fatter in all the examples we have seen.
right. So should we? I mean, when we say that okay, Laplace is better, so in the graph, if we see it is student t is better. I mean, what
No,
judgment
no,
you
I
can
didn't say
predict from
Laplace
this?
is better. I'm saying Laplace
Uh,
is popular.
okay. Okay, fair enough.
Yeah. Any other question? Feel free to ask questions, by the way. I mean, these are for this. Yeah, someone was saying something.
So what actually the degree of freedom is doing here? I mean, it's you said in last slide, it's trying to
Degree of normality.
yes,
So
degree
I
of
just, yeah, so let's say this black one is normal distribution,
yes.
and you look at this tail of this black distribution, it is very, very low. The lower it is, the thinner it is. So that's what we call thin tail.
Okay.
Now, let's say if I wanted to like increase the like I want to make it heavy tailed, right? So
Yes.
I choose a student t distribution. Directly it shows you that it's heavier tailed. Now, let's say you want to adjust the tail, you want to lower it for student t. You increase your degree of normality, which is DOF in this case. So if you increase the degree of normality, the tails will become thinner and thinner till it hugs this normal. So you have that extra control,
Okay.
right?
So it is averaging or something to, I mean, to include the data inside the Gaussian.
It's not averaging. So
okay.
what is a distribution, right? So on the x-axis, you have all the values which data point can take, right?
Okay.
Now, if you plot a histogram with very, very fine bins, infinitely thin bins, let's say, if you plot the histogram, it will give you a distribution. What a heavy tail means is that there was actually a lot of values in the tail. That's why it's heavy. It's not just
Yes.
heavy for random reason, right?
Okay.
So, so yeah, one more thing is like robustness, but it's also about modeling that. Do you think there's a lot of things away from the mean? If it's the case, you need something like a heavier tail. Maybe
Got it.
calling it outlier is not always good, but being heavy or not is always the case, right?
God. In the next
And-
slide, but it's okay. It seems like you are avoiding that outlier. I mean that the
Yes.
model is
So
even the
in
student
most
T
of
is
the
avoiding it.
cases, yes. So in most of the cases, when we try to estimate something like the mean or something, we don't want the mean to be too much affected by the outlier if that's the outlier.
Okay.
But there are applications where this is not an outlier. It comes from some natural process or something.
Okay.
So maybe then you want the model to be affected by outliers, or if you want to model it. I mean, it depends. I mean, for example, in linear regression, you want to avoid outliers, but maybe you want to model outliers. So maybe it's the same thing, maybe it's not. I mean, it depends on like use case. Not able to think right now, but the point is, if you have a lot of data points away from the mean, then at the least I can say that the tail should be heavier. Outlier or not is subjective.
Okay. So this degree of normality, like how long it can be, how big number it can be, like it can be infinity.
Yes.
Zero. Okay. Thank you. Got it.
It can be very, very high value. It can be infinity.
Okay.
Yeah.
Thank you.
That's why I'm saying it's tending, right, in the previous slide. So from 1 to 2, when it became, it's a big jump. But as you make it 10, it will be very close to this. If you make it 100, it will shift very slightly. If you make it 1,000, it will shift very slightly again. So after some time, it's almost hugging it. Increasing it doesn't change a lot.
Okay. So
But
my
yeah,
motto of okay. So my motto of this DOF is to try to make it as a Gaussian, right?
No, yes. Basically, degree of normality or degree of freedom is giving you an extra control.
Okay.
So for example, if there's no outlier in the data, then it's okay.
Yes, we can use Gaussian.
Yeah. Even here, right? When there was no outlier, you can see all the tails are thin.
Okay.
Right?
So in this case, like both, okay, then both Gaussian and T and overlap, both lower, right? That's what's happening. Okay, got it now, got it. Thank you then, got it.
So data is helping you decide degree of freedom.
Got it there. Thank you.
Okay. So there's something called an empirical distribution. I'll show you the plot in the next slide. But let's say you have a one-dimensional data set. So it's just real numbers. So let's say you have data set of size n called capital D, and it has n points x1 up to xn. Now this delta subscript xi is a function which says that at location xi there's a delta function, and if you take average of all the delta function, that's your empirical distribution. Now this CDF, another thing about a property of delta function is that if you take the integral of a delta function, you get a unit function. It's called unity function or unit function. But yeah, basically that's the CDF. How it looks like is in the x-axis you have all these data points x1, x2, x3, x4, x5. So the empirical distribution is just these arrows, these delta functions, right? So that's your delta function, and if you take an integral of it from minus infinity up to a particular point, that was the definition of CDF, right? What is the probability from minus infinity up to that point? That's the definition of CDF. And if you do that, you can see that at every data point you get a jump, and the height of the jump is 1 by number of data points, right? So that is what empirical distribution is, and the PDF and CDF of empirical distribution looks something like this. Any questions? Okay. So next thing we looked at in the lectures, this is mostly revision part. We looked at transformation of random variable. So basically you have this CDF f of x for random variable x. You know the transformation, which is g of x, which transforms this random variable x into another random variable y. So this f is known, this transformation is known. What is unknown is what is the density function of my random variable y. So that's the goal. So this red circle is the unknown. So it's a two-step process. First you find the G inverse, and your CDF of y is just your CDF of x, and you feed in the value of x as G inverse of y. So that's the first step. Second step is you just take the derivative of your CDF of y, and you get your CDF of you get it, right? The relationship. And this is what I just said. The two-step process. The first step is f of y. So the step number A is just saying the definition of the CDF of y, which is just p of y is less than equal to small y. Now you can substitute y is equal to g of x. You can take the inverse on both sides inside. So you get p of x is less than equal to g inverse of y. Now, basically this is the definition of CDF again. So you can substitute CDF of f of x, CDF of x with the value g inverse of y. So that's step one. Step two is just find a derivative and you get your answer, because PDF is the derivative of CDF. So basically that's a two-step process. We have seen in the recorded videos. The next one is generating. Okay, any questions?
No there.
Okay, so the next one is generating random numbers. So again, if you know the probability, usually there is a way to generate data from that distribution. and then you can plot it, whatever. So that's one path, that you have a generative process that from a model, given the parameters, you can generate data. Then there's a reverse process of estimation, that given your data set, you can do estimation and find the parameters of the model. And it feels like Bayes rule, right? So the likelihood function, what it is doing is that given the parameters, you generate your data. That's your likelihood function. Given your data, you try to estimate your parameters. That's the Bayes rule. So kind of left hand side, right hand side are connecting here in this, right? That's one thing. Now, how do you generate a random number? The diagram remains the same. The unknown has changed. So earlier we had our input distribution. We knew our transformation. We wanted to find the output distribution. Now we have changed the unknown. Now we have simplified our input distribution to be uniform. We know our output distribution. What we don't know is what is the transformation. How does this help me? Because all libraries, all programming languages provide you a function call which gives you a random sample from a uniform distribution. And the CDF of a uniform distribution looks like this orange CDF. So to generate random number, we fix our random distribution to be uniform. We know our random variable from which we want to sample, or we know our distribution from which we want to sample. So first thing what we do is we integrate our PDF to get our CDF, capital FX. Once you know your CDF, you find the inverse of your CDF, and that inverse is just a function. Now, how do you generate random numbers? You generate random numbers from your uniform distribution. You pass those random numbers through this function. The new numbers which you get are random samples from your f of x. That's the process. And we had seen the derivation in the lectures, how this is true. And again, I'll just repeat the problem, but we have more insight into what we were doing before. So again, the question is, given a distribution, a discrete p probability mass function, we want to sample from a six-sided die with probability p1, p2, p3, p4, p5, and p6, a vector of 6 probabilities which sums to 1 and is positive. So we want to write a Python program to sample from this distribution. It's the same diagram we have seen before, the intuition. So we have our PMF, we find our CDF, and what is a forward CDF? You give me a value, I go up, I go left, I get my value. What will be my inverse CDF? I can go from my y-axis to x-axis, that's my inverse CDF, correct? So I generate a random number. It will give me some random number between 0 and 1. And my inverse CDF is basically I go back, I go back, I go back. And I basically get a value, which is 5. And if I go back in this way, it's kind of behaving like an inverse CDF. And an inverse CDF of a step function is exactly this. It's like a collection of if statements. And this was the code. So I told you right now, right, that the inverse of a step function is a collection of if statements. So that's what it is. So again, it's simple. I have my P. I find my CDF. I want to sample using the CDF. So first I generate a random number from a uniform distribution between 0 and 1. That gives me a U. And then I have like a collection of if statements which returns me the right answer, let's say. So this part is actually my inverse CDF. This for loop is my inverse CDF, right? So it's the same answer which we have seen before, but we know more about it. What is happening? What is happening? This is happening, right? It is just that for discrete distribution, the inverse is more complicated. It's a collection of if statements. So we have to search for it. But if it's a continuous thing, it's just a transformation. And we have seen multiple examples of continuous F inverse. Like I think normal we had seen exponential also. But anyways, we had seen it in the lectures. So now we have like a deeper insight into what this code was really doing. So that's all about today's presentation. Any questions?
No, there.
Okay. So I'm done with my today's presentation. I'll just stay for a minute or two if you have any questions. Otherwise, we can end this call.
Dev, so many of the distributions are I mean, you can start from one distribution and you can land up into another distribution by changing the parameters. So, I mean,
Shape wise, yes.
yes. I mean, there will be some parameters which will, if you pull it down or up, it will change the focus shape and you will land up in another kind of distribution. So, is there any interconnection? I mean, just wanted to I mean, not here.
So not always.
Mhm.
Yeah. So basically, a lot of distributions have relationship to each other. So for example, here we had already seen gamma and chi-square is related. Then how chi-square and normal is related. And natively normal and chi-square should be related because chi-square is built from sum of square of normal distributions with k number of things, right? So k is my number of things I'm adding. And then there's some lot of, so gamma we had already seen in the lecture. It's also related to exponential in some way. There's something called Erlang, I don't know what it is. There's something called Rayleigh, Maxwell, whatever. So the point is there are gazillion distributions which are related to one another. Sometimes it doesn't tend to it. It's exactly like you substitute this value and it flips to that. There's no continuous way to go there.
Right, right.
Okay, fine. Any other questions? Okay. So yeah, so next week, just week 12. So these three videos you have to watch. Sum of two random variables, random vectors, high dimensional Gaussian. That's for next week. I'll post it on the group also. I'm just letting you know here. Because usually I post it like 1 day, 2 days later. But yeah, this is what you have to watch. Any other questions? Okay, fine. I'll stay for a minute and then I'll end this call. Thank you, everyone.
Okay, thank you.
Thank you, Dev. Thank you, everyone.
Thank you.
Okay, there.